And welcome back. Furthering our exploration of hemiacetals and acetals. We are going to look at the hydrolysis of acetals and thioacetals, also known as deprotection. We looked at them and we used them previously. We just didn't do a mechanism yet. And you know, this book is still in development, and I notice an inconsistency here right from the beginning compared to when we created this carbonyl oxonium before. And when we did that, generation of the second carbonyl oxonium, and I was very specific. First, I said, you can't make that OH leave until you protonate it first. That's what the black arrows meant. And down here, I actually showed it. Where was I doing that? It's there. I said, you can't make this OH leave until you protonate it, which I did specifically by itself. And then I made it leave. And I notice in my new one, which I'm going to try to fix today, if I can remember after class, and I'll show you exactly what it's going to be. And you should feel free to fix it in your book as well. I'm going to judiciously try to use my pen here. If my pen was on, I could use it. And we're going to get, you know, I need white out for white and gray out for gray. It's really, yeah, here we go. Get some gray right there. I'm going to pretend this arrow did not start here. Yeah, I need a little thicker pen. And it turns white. Yeah, what can you do? I think I did a good job. First step in black. Whoa, that's a nice electron there, isn't it? Lone pair. That's where the arrow starts. And in gray, second. It's not even funny, is it? You're going to have to pretend that's gray. I don't know what to do. I think if I draw it down here, and then move it on top, oh, it doesn't show up either. My computer's smarter than I thought. How about blue second? There we go. We'll get through this. Bleu. It's French. No, then it goes over the lone pair. We can't have that. Hey, won't even let me control Z anymore. I saved. It's becoming a nightmare. Okay, so what I'm trying to say is blue arrows first, second, and black arrow first. Lone pair protonates. Then you boot it off, and you get to here. And I'll do exactly what I said down here, so you can't say, oh, I couldn't understand that. That was a disaster. What was he doing? I'm going to do it down here without disasters. What was the first step? And we're going to do red first down here. Blue second. And the first was to protonate the O you want to leave. And there it is, protonating the O that I want to leave. And the second was the lone pair on the O coming in baby blue, kicking off one of your ethanols. So right now I've accounted for one ethanol that I see over here. There's two when I'm done. And one of them goes right here right now. And we've generated this species here. Oxonium, activated oxonium. Activated for what? For attack by a poor nucleophile. Now you're not going to use ethanol as your nucleophile. You're going to use water. Water is a poor nucleophile. And I can do a time saver here for you. The water will attack. And the sulfate ion you generated here in the next step, what does it do? Let's see, water's attacking here. Next step, the toluene sulfonate ion neutralize the oxonium. Do it in a separate color that's blue. You're saying this is in the next step. And you will have, I don't know, this it's doing stuff I don't want it to. Okay. We're going to have not an oxonium because we skipped drawing that step with our two-color shortcut. And we have, what do you call a functional group that has on the same carbon an alcohol and an ether? Yes, it's called a hemiacetal. It's the intermediate in both reactions that make acetals. It was halfway, and takes an acetal and does hydrolysis. So if you're not drawing the hemiacetal somewhere in the middle of your mechanism, you have done something wrong. And can we get to the product? Let's see, where are we right now? We did this. We got this. We neutralized this. Now, what's going on up here? We're protonating first to make a better leaving group. Got it. This has to go. And then we're doing, what do you call it? When you grab an H, take an old sigma and make a pi and kick off a leaving group. I want you to think about that. I'm going to give you the answer after I draw the whole mechanism. What do you call it when you remove if I gave you our old letters of Greek alpha beta? Here's the carbon with what's going to be a leaving group after you protonate it. Call that alpha. Next door is an atom that's called beta. Beta's losing an H and you're making a pi. Have you come up with the word elimination yet? I hope so, because that's what's happening. And we're going to use the catalyst conjugate pair of sulfuric acid and its conjugate base. We'll put the base up here closer to the hydrogen. We'll put the acid here because that has to make the other ethanol leave. The first step is to protonate the O you want to leave first. That O has to go. It'll be the second alcohol that leaves. It will not leave until it is protonated and therefore a better leaving group. So you could draw that protonated O right now if you want and then do the elimination step, or do it as on the top of the screen and go straight to it. Grab H, sigma becomes pi, leaving group gets kicked off, but I used red. Oh, I'm not allowed to use red. I'm supposed to use a separate color to acknowledge that this is a second step. It's okay. Give me an opportunity to show the arrows again. There. Oh. Elimination. Grab H, make pi, leaving group leaves. And there you have the deprotection of the acetal to make the carbonyl compound again. And we need to know that mechanism for our exam, all of our exams. And we're going to finish up. I forgot to copy it over. Thought I did it. And don't know if I want to start that whole new section and try to squeeze it in 10 minutes. So I don't want to start a new section. Let's just do a little acetal, hemiacetal review. And I thought of a nice example just now. I want to provide a full mechanism. For this process. And 1, 2, 3, 4, 5, 6. And we'll put the mechanism down here. It's got a nice clean blank at the top of the screen. And I'm going to combine as many steps as I can down here. Once again, a reminder, we'll do red first. I'm getting some stuff. Okay, tell me how I did that. Trying to teach me a new line. Wow. Red first. Blue second. And we have to make an acetal over here. How do I know this is an acetal? It's a carbon that has an ether in one direction and yet another ether in a different direction. That's an acetal. I thought we needed 2 alcohols and a carbonyl to make an acetal. We do have 2 alcohols and a carbonyl. Here's the carbonyl. Here's alcohol number 1. Here's alcohol number 2. Yes, the alcohol can be in the same molecule as the carbonyl. That will be an intramolecular reaction, won't it? Which brings up a good point that I wanted to talk about. Your first step will be in red. What is this first step? Why are we doing this first step? Why are we protonating the carbonyl oxygen? Because we need to activate it. And I want to combine that with the next step. What was the reason of activating the carbonyl? Why did you do it? So it could be attacked by a poor nucleophile. What are our poor nucleophiles? What are our poor nucleophiles? Got it. We have alcohols, both poor. Alcohol, alcohol, poor. Which one will react faster? The one that's in the same molecule already close by, or the one that's an external alcohol, a separate molecule? I think I implied the answer in the wording of my question. And yes, if you did the other alcohol first, you could still get full credit almost, but I got to deduct a little bit. Half point probably. If you went with the other alcohol right now and did all the mechanism steps appropriately thereafter, you'd still lose a half point because you're not acknowledging that an alcohol in the same molecule that's going to react and make a very nice ring size. If you want to review ring sizes, 6s and 5s are really nice ring sizes. I would not have this argument if the ring size was 4 or less. I'd go the other way because those are strained. Do you remember that stuff? Strain. We just talked about it in Orgo 1. And this is an equilibrium process. And oh yeah, we got to move. I combined my 2 steps. I have the O here that still has an H on it. Oh, wait a second. Time is now a factor. If this drives you crazy, then don't do it this way. I'm going to go green 3rd. Third. You're going to make that ring. I haven't shown you the green step yet. You're going to make this ring here. And I'm not going to draw the H that's on the O, but you're going to have this. Oh, and my product was wrong too. I missed a methyl. Somebody's going to point it out. It was very polite of you not to point it out. Yeah, there's a methyl on the carbonyl. There's still a methyl on the carbonyl. And what do we got? How many CH2s? 1, 2, 3, 4. 1, 2, 3, 4. We've got this, except the next step is to neutralize the oxonium that would be right here. And if you do that in green, you're saying, I know that's a 3rd step. Look at that. And don't forget, you attacked a carbon and made an O that has an H. That's still there. And you went right to the hemiacetal, didn't you? Remember, you got to make water leave. And what's the first step? Every time you have to make water leave? If it's not a protonated O already, you must make it so. First step, protonate the O. Second step, make it leave. That's baby blue. Your water is gone. So notice your dehydration happened. To bring a point to my biology colleagues that was mentioned earlier, you did the dehydration before you made the molecule bigger. You did the dehydration before you did the synthesis. Perhaps it should be called, oh, wait. No, the synthesis was here. Okay, my biology people are fine. We're talking condensation and synthesis, and I really don't have a problem with that. And where are we at? Propanol needs to come in. We're going to finish this off. You think we're out of time? If we employ our multiple steps, draw that H bonded to O, lone pair. We have an activated carbonyl. We're going to attack it. And then we're going to neutralize. We're going straight to our product here. We're going to neutralize our oxonium with the OTS minus, and somebody was going to point out, I forgot an arrow here. Ooh. When we made TSO minus, that's going to neutralize an oxonium that the red arrows would make right here. And that will be done in baby blue. And you have generated your acetal. And in the book, if you read about why did I choose this alcohol to attack and not the propanol, a gentleman named Eschenmoser will be invoked. And he says an intramolecular reaction happens faster when it makes a nice ring size. than an intermolecular reaction, so it will happen first. And that brings to a close today's discussion, largely focused on hemiacetals and acetals, but begun with our discussion of hydrate formation. So I'll see you Wednesday, and we'll start talking about test 1 and problem sets very soon. And keep doing your owls and reading the book. Hopefully you finish chapter 16 already now, or continue reading it and have it done by Wednesday. And I will see you then. And goodbye.